the high-tech equivalent of a musical instrument. Think of a violin, a piano, acoustic guitar. How do those technologies work? It's not like a conventional loudspeaker that we're all very familiar with, which in essence is a cone-shaped device which operates as a piston, moving backwards and forwards in a very controlled fashion. We've had that for 100 years. But think about those natural musical instruments. We've had those for millennia. Those devices don't move, or at least you don't perceive that they move. The strings themselves don't generate the energy that we are listening to, because otherwise the electric guitar would work. The strings send their energy with the tones and the notes that we want to play through the bridge of the device into the soundboard of the instrument itself. And in the shape of the violin, for instance, that's a stiff, very lightweight wooden structure. And that wooden structure vibrates across that whole surface area, such that if we actually took our hand and placed it on the instrument whilst it was being played, we would feel the vibrations happening in that surface. And that instrument and the surface that's vibrating connects with air in a much more effective way than the piston-shaped cone that we're familiar with connects with air in terms of putting acoustic energy into that air itself. And so think about the violinist in a concert hall. How is it that the violinist is holding this instrument very close to the ear and to the head, but yet is not deafened whilst playing the instrument? Yet we in the audience hear that very clearly right to the back of the concert hall. That wouldn't be true of a small conventional loudspeaker held close to the head. We wouldn't be able to hear it, and worse still, that instrumentalist would actually be quite deafened if in attempting to do so. And the real reason why those musical instruments, those vibrational surfaces, are so effective at adding energy, acoustic energy into real space, is first of all because they are not directional devices. We're maybe familiar from the conventional loudspeaker with our hi-fi systems. We put our two speakers, we toe them in slightly, sit right in the middle. That's the very best place to listen to our product. That's called a sweet spot. And we might be familiar with a retail type of environment where we have a ceiling speaker. Under the speaker itself, it's very good. As soon as we move away, that tone changes dramatically and the energy falls off dramatically. And that's because those devices are highly directional. The natural piston and the physics of that piston mean they're directional devices. The vibrational instrument, by contrast, is sending energy in a full 360 degrees from its surface, front and back and all over. That energy is then sent out to the first boundaries of the concert hall. Some of that energy reflects back in. Now again, the conventional loudspeaker and this ideal piston forms energy, and it's a complex area to get over, forms energy in a state of phase relationship. And the ideal way to look at that is to think about a pebble dropped into still water. We're all familiar with what happens. These nice concentric rings of energy flow out from that point of entry. That's phase relationship. And we all know that when that water and those energy rings when those waves hit a boundary and come back in, some of that's reflected and starts interfering with the original waves, such that you have perhaps waves that are twice as big, or perhaps waves that are cancelled altogether. And that happens exactly the same in a sound environment with that conventional loudspeaker. Sometimes you'll get double the energy because it's actually overlapped and added together at the same point of phase. Sometimes that's cancelled. So in a real space, the actual sound you listen to is often different to the sound the loudspeaker is recreating. And that's because of the reflective effects of the boundaries.